Swayam Prabha. Digital India. Educated India.
Good morning, welcome to the course on intelligent product design, design practice, and today is the third lecture in which I will give you the concluding part of the overview of how we actually make intelligent products. Okay. So, once I give this overview to you, then we will be able to start the foundation of the course. So, what we have discussed in the last lecture, if you remember, is that when we talk about an intelligent system, we not only talk about robots, because robots are not the only intelligent autonomous system or IAS, but many other autonomous systems exist. For example, I told you about unmanned air vehicle, I told you about unmanned ground vehicle, I also told you about these autonomous underwater vehicle AUV, autonomous underwater vehicle. These are some examples of autonomous transportation, and similarly the hyperloop. So, these are examples of autonomous transportation. In the last class we have talked about it. Then there are these surgical platforms like Da Vinci. So, this is like a healthcare device. Then there is this autonomous tactical swarm system, which is used in autonomous weapon systems, or AI driven Northrop Grumman X-47B. This is also an autonomous weapon system. There are also some examples of fun and entertainment systems, such as Sony's Aibo, which is a robot dog, and Anki's Cosmo. Cosmo is here. It has some emotional intelligence also, which I will talk about towards the end of this lecture. And also we have some other examples of AI and VR games like Half-Life Alyx. So, certainly all these examples that I have told you, they are not examples of robots, but yet they are autonomous systems. So, such autonomous systems we will learn through the course that how to design, what are the basic foundations of designing such systems. In the last lecture, for your quick recapitulation, I have also talked about significant intelligent systems. For example, I have talked about these BI, CI, EI and PI, right. BI stands for biological intelligence, CI for computational intelligence, EI for embedded intelligence and PI for physical intelligence. If you remember, I told you that today whatever is the most popular form of AI is in the form of artificial neural network, convolution neural network, etc. These are all examples of CI, but soon it will be replaced by EI and PIs. Now, what are the key characteristics of an EI system? First important characteristics is that it can do real time processing. Systems can gather and process data quickly for immediate action. And another advantage of EI is that it can be integrated with the AI. So, use of machine learning algorithms for decision making can be done with an EI system. Further, EI system needs very low power consumption. So, it is optimized for efficiency in energy constrained environments. And as a result, EI systems, we find their applications, it has started to come today in the fields like Internet of Things, IoT, which are all sorts of smart home devices and industrial automations, and wearables, smart wearables like health monitoring devices. Many of us keep the smart watch with us, which monitors our health. So, this is nothing but an example of this kind of intelligent system okay, embedded intelligent systems. Then autonomous systems like drones, self-driving cars and robotics, of course, it is there, and the healthcare issues like advanced prosthetics with integrated sensors and processors. So, these are some of the examples of the EI. Now, if I look into PI, key characteristics of PI is that it is material centric design. So, PI or physical intelligence focus on smart materials, such as some examples are like shape memory alloys, hydrogels. I have talked about the application of shape memory alloy in the last lecture, and soft robotics. So, this is one important thing, that PI, which is physical intelligence, actually talks about material getting involved in the design. So, it is a material centric design. Then the second important point in PI is that it has autonomous behavior, very similar to biological system. It can adapt without external computation, driven by the properties of the material itself, it can adapt. And then the third important property is that it is bio-inspired. It has many applications which are bio-inspired mechanisms, like mimicking nature, such as self-healing materials or materials which has tactile sensitivity. So, these are some of the key characteristics of PI, and their applications are in the fields of soft robotics, biomedical devices, sustainable materials, space explorations. So, these are some of the upcoming applications of PI. Now, today the direction in which we are going is actually a convergence of embedded and physical intelligence. So, we merge the EI and PI together and take the best of it. For example, one example of such hybrid system is the soft robotic system with embedded AI. So, such that the two fields merge. So, you have integrating sensors and actuators into soft bio-inspired robots for real time environmental interaction. Then we have self-sufficient systems, which means the systems are energy harvesting. That means, they take energy from the ambient itself. You do not have to supply energy by sort of direct energy supply. It gathers its own energy, and this is done with the help of smart materials. I will show you an example of such a system. Then the third one is the wearable technology, which is coming up very rapidly. Devices that can adapt their physical properties like stiffness, like temperature, based on embedded intelligence and physical intelligence. Okay, we are today talking about, for example, jackets. There are jackets for high altitude applications for defense, where the jacket can control the temperature, the insulating property in a manner that if outside is very, very cold, then it automatically insulates to a very high degree, and if outside is reasonably hot, then it works the other way around. So, this is example of wearable technology where EI and the PI meets together. Then of course, there are these examples of swarm robots, where it is a team of decentralized robots that use the embedded intelligence for some collective efficient tasks. Now, some examples of physical intelligence also I talked about in the last class, and I told that one great example is what we have done in terms of developing this actuator with the help of shape memory alloy, okay, material which can memorize its shape, and hence we can take the advantage of it to create a back and forth motion. That is what this system does, and we can use it as a linear actuator. I now want to go little further today. So, I want to talk about certain soft materials based grippers that we are developing, and in all such futuristic applications, we not only need artificial muscles, which is a part of general physical intelligence system, but also we need a compliant structure or a soft robotics as the carrier of such a system. Now, how do we develop such a system? Well, three important elements of such a systems are metamaterials, programmable materials and microstructured auxetic materials. I told you that materials is one of the very important consideration for the design of intelligent systems. So, let us look into it that what are these new materials? Well, first of all, if we talk about metamaterials, these are exceptional class of synthetic materials having different types of very interesting properties, which you will not see in general, like call it idiosyncratic properties such as stiffness becoming negative, okay, or Poisson's ratio becoming negative. What does it mean by having a negative Poisson's ratio? Well, we know that if we take a sample, let us say, which is not a metamaterial based sample, but a simple material, and we apply a force like this. So, we expect that the material will elongate in this direction, but also as you can see from my drawing that but also it is going to contract. So, in this direction it is contracting, whereas in this direction it is expanding. So, this is when you have a positive Poisson's ratio. So, this is positive Poisson's ratio. Now, how can we have a negative Poisson's ratio? Well, you just imagine in comparison to this, you have something which we call a kind of a structure like this, a structure which is opposite to a honeycomb structure. So, auxetic structure. So, now if you apply the load, you would see that it will not only expand, but also it is going to expand the transverse direction also. So, this can be something like this that is going to happen. So, here you are going to get a negative Poisson's ratio. Now, metamaterials, you can actually generate all these things by having a systematic repeated structures, like you can see it here that there is a systematic unit. This unit is repeated n number of times, and what is there in unit? You have a mass inside which you have another mass. So, we call it as a mass in mass system, something like this. Or you consider this structure, this is also repeated in nature, and you see that what you have is this mass which is added with this system with the help of some springs. As a result, this whole thing behaves like an array of a Helmholtz resonator, and you can create negative stiffness from this system. I will talk about the exact technology later on. Now, what is the advantage of it? What are these metamaterials? How do we define them? So, these are artificially crafted materials that derive their properties from their internal microstructure, and internal microstructure will have such repeated units, okay, repeated units for n number of times. And as a result of that, if you excite this structure from one side using a vibration, you would see that in certain regions the vibration will propagate. So, this is the propagating zone, these zones are propagating zones, this is also propagating zone, but if the frequency touches 300 hertz and up to 500 hertz in this particular design, you will see no wave is propagating to the other side. That means, even though I am, let us say, exciting, sending a signal, nothing is coming out here, okay, very strange, as if the entire structure is absorbing the energy somehow, and that is only going to happen in a frequency band which we will call as attenuation band. So, metamaterials can show such attenuation band, and that is something like in a optical domain we call it like a, if you have seen Harry Potter, the invisible cloak of Harry Potter. So, that the light is falling, like you can see me because the light is falling on me, and then you are getting the light back to the camera, but what if I absorb the entire light inside, so that nothing goes out. So, then I become invisible. Very similar to that, sound wise or vibration wise, you can create this invisibility using these metamaterials. So, they have applications in vibration control, wave absorption, wave tuning. For many such things, it has become inevitable to use such a system. So, this is one application where the two things merge. That means, there is an attenuation band, but can I control that attenuation band willingly? Yes, we can do that. So, you can shift it whatever you wish with the help of some smart material that you can integrate in the system, you can do it. Now, what are the applications of such metamaterials? Well, you see, in space there are applications like multi-scale systems. In robotics, there are applications like this robotic octopus, this other type of soft robots. Then the medical, there is this ultrasonic imaging and meta implants, there is a application. Defense, there is a major application in terms of different types of vibration control, shock control, etc. In automobiles also there are applications. So, for an intelligent system, metamaterials is coming up with many big applications. Now, such repeated structures are not only available only by our some designs by ourselves, but if you have a curious eye, like here I show you that what we have discovered recently, that one of the mausoleums is having actually many such kind of metastructures embedded in it, many different forms. You can see that 9 different patterns we have been able to discover, and each one of them with the help of certain modifications, you can actually create this attenuation band gaps in it. So, keep a curious eye for looking for this kind of periodic systems. Here you see, with the help of certain additional mass, we can actually create this attenuation band. So, you can create such attenuation bands in many such systems, and today we are using artificial intelligence to actually study first that how different patterns create different types of transmissibility, and later on we actually give our own transmissibility as input, and the AI comes up with the pattern with a predicted metastructure, that what kind of a repeated pattern we must have in order to have this kind of a transmissibility. So, that is how we are progressing very fast towards the merging of physical intelligence and embedded intelligence. Now, I told you that another important material that plays a big role here is called a programmable material, which is in terms of honeycombs, and these honeycombs are special honeycombs because these sides of the honeycombs are having a smart materials attached to it. What does these smart materials do? What is the significance of it? Well, very simple. With the application of voltage, they can actually change the angle, so that you can get different angles in it, and if each one of these lattice changes its angles, your stiffness changes drastically, and many other properties. Like you can see here, with the application of voltage, you change the stiffness from 10 to the power minus 8 to something which will go to say something like 1000 or so gigapascal. So, there is a huge change that you can do. You can do it in unimorph, you can do it in bimorph. Well, in one of our papers, we have talked about that how this technology can be done, and in the class we will gradually learn at least some of these techniques. Now, I told you that another way of application of this PI and AI together is in terms of developing green energy solution. For example, wind energy is one of the green energies. Now, traditionally we use wind energy for turbine based wind power generation. However, instead of doing that or solar energy, can we have a better solution in terms of energy harvesting, not in terms of turbine? So, we can do it, particularly whenever the wind speed is less, it is not so high as say 20, 30, 40, 70 kilometer per hour, but slow wind speed. We can do it with the help of a technology which is called vortex induced vibration. There is a product that has been already developed in one of the universities. It is called Vivas, and it is used not for wind, but for water flow, and it is suitable for such low flow velocity 0.5 to 6 kilometer per hour. And what it does is that the flow of the stream creates a, like the flow is coming here, it is creating, because of the blob body, it is creating an oscillation, and that oscillation is subsequently extracted in terms of energy harvesting. So, this is a VIV system that we have developed in our laboratory. You can see that the wind stream is coming here, and from this direction the air is coming, and there is this blob body, and because of these winds creating the vortices here like this, it is going to have an oscillatory motion that you can convert in terms of energy. Now, you need not only do such things for solids, you can do it for liquids also, and which you can apply for a liquid robotic propulsion, drug delivery, or something, a product for even cleaning up the oil spills at sea. So, you can see that when I normally drop a liquid drop on water, it actually coalesces in the water. But in a specific case here, if I can create a vibrating pattern and then I drop the liquid, you would see that first of all the liquid drop will get bounced here, like this drop in this experiment will get bounced from here. So, this is something that will actually create a tapping motion. So, that this ball, instead of getting coalition, it is going to get tapped continuously. And then you would see beyond a certain frequency, you can actually create a pattern on the water, and this fluid can actually travel in this circuitous pattern, creating a zigzag trajectory. You can control that trajectory. So, this is a zigzag trajectory control system, and you would see the y and x coordinate, which clearly shows that some kind of a path is coming up in the system. Now, I finally come to another final aspect of this, which is the emotional aspect of a design, and this is using child robot interactions, some of our experiments. So, this is using a now robot, which has again multiple sensors like acoustic sensors, 4 omnidirectional microphones, 2 loudspeakers. Then it has also the touch sensors here, and also it has its own computing power. So, it has its own Bluetooth connectivity and all the degrees of freedom with the actuators. Using these, we have done experiments that can we create a trust between a child and the robot. Okay. So, that is something that is extremely important for an emotional design. So, here we have designed a game for the child, and which is certain sequences of the game, and the robot actually plays with the child, and at certain stages the robot asks for energy, and then if the child reciprocates and the robot helps, then it is a good part that the trust is developing. Sometimes the robot actually works like a betrayer. So, it defects. So, there are different strategies of betraying, and through that we try to study that how the trust between a adult or a child, how that is getting affected. So, this is the game in which they play, and once they play this game with now, we start to model the trust scores in the system. And we see here that even though the robot actually defects, for the child, if you compare between an adult and a children, you would see for a quite some time, long time, they actually hold on, they believe the robot, okay? They have more trusts. The other aspect of it is the emotional aspect. So, how do an intelligent system would show certain emotions like say happiness, sadness, anger, surprise, disgust, fear, neutral, how do they show? Well, we told the children themselves to show how, what are different sorts of such kind of things, and then once they do that, then we start to actually play it and we start to map that different emotions. And once you map the emotions, we program the now robot so that it can play with these emotions. And then we see that once these emotions are there, we can see that the robot itself plays these emotions by copying from the child, and you will be able to see that all the moods like happy, fear, surprise and sad now is playing, and there is a good kind of a mapping between the now's emotion and what the child recognizes as a recognizable emotion in the system. So, each one of these modes you will see in the video that now has been able to actually follow these emotions in it. I now come to the future directions of intelligence. So, that is the final point, that there are issues that are coming up in the intelligent system design. One is of course, the design complexity, like crafting autonomous systems with embedded intelligence would require an interdisciplinary effort. The knowledge of material science, mechanical engineering and control system has to merge together. Then there is issue of what we call control structure integration. So, that you need to have a balance between how much of computational control and how much of structural control you will be able to have in a structure, in a system. And then there is a question of scalability, that is many such principles are valid today in a smaller scale, whether at a bigger scale you can jump in order to have the same activity. And finally, there is the materials development, like creating advanced materials that can further enhance the physical intelligence. So, all these four issues together actually are the way forward towards the design of intelligent systems. I would like to collaborate, acknowledge all my collaborators whose work based on which we have, all the slides that I have shown you, Professor Alpar, Professor Sandipan, Professor Arnab, Dr. Ankur, Dr. Amanpreet, Dr. Vivek and Mr. Kanaiya, all their works together I have shown you here in this slide. So, thank you, and with this we will complete our overview of the intelligent systems, and we will come back to the fundamentals of how to do the design concept generation, and that is the thing that we will tackle in the next class. Thank you very much.